Okay, so let's try to prove this. So this is going to be about the sum of functions, and it's essentially that if what we're trying to prove is, say we have a function and we know that function g, it's in the big O of f, then we know that f plus g is also in the big O of f. So let's get right to it then. Let me scroll down a little bit. Okay, so then let's get started here. So let's write out what this actually means. So let's expand both of these. So we have, oops, I don't want that. Okay, so we have f, g. So this means we have two functions, f and g, and they map from natural numbers to positive real numbers. And then let's have the first part. So we have g is larger than this, so this, okay, so, and we're gonna write c1 and n1 here so that we can differentiate, because we'll have two big O notations or big O statements to unpack. So okay, so n is larger than or equal to n1, then g of n smaller than or equal to c1 times f of n. Okay, and we have this whole statement, which is this right here. Then we have implies, and then same thing really. We just have c2, n2, part of the real numbers for any n such that n, and then this time it's n2. Then finally, okay, this is, we want to make sure we get this right. So we have g of n plus f of n is smaller than or equal to c2 times f of n. Okay, so now that we have this, let's prove it. Prove. So let's take care of this. Let f, g, natural number, real numbers. Okay, and let's assume g part of whole f, i.e. that, you know, we have this whole statement here. We'll just copy this over. Oh, not so easy, it seems. There you go. Okay, so we assume that, and then let's see here. Did this get messed up by the, yeah, a little bit. Okay, so we assume this, and we want to show that f plus g is part of this, i.e., then we'll just go ahead and try to grab this. Ah, look at that. Okay. So, like before, we just need to follow the structure and go step by step. So we already have this part. Now we've assumed this. Okay. So we have this statement and we know that this exists such that this condition is true, but we don't necessarily have access to it yet. So let's first unpack assumption. Okay, so we let c1 and n1 that satisfies, oh, I think this needs to be plus, satisfies our statement Okay, so this would we're just saying I'm going to call C1. So this is saying that there exists a C1 and an N1 such that this condition. So we're going to say, oh, I'm going to call C1 the C1 that they're talking about here, and N1 they're talking about here. We know that these are numbers, but we don't know what exactly they are, and it's fine. We don't need to know. So next we need to unpack. So okay, let's let N be a natural number. Then we assume N is larger than or equal to N1. Okay. And then we know that G of N smaller than or equal to C1 times F of N. So now we have access to this. Okay. So we want to show this. So now we want to show, so we need C2 to be something, and we need N2 to be something. We don't know what yet, and it's okay that we don't. It's actually perfectly fine that we don't. We just write out everything in the right format, then we look at it and we see what parts are missing. That's the wonderful thing about existential proofs, really. So let N, okay, so this N is already satisfied here, so we don't need to take care of this. We just have to assume that N is larger than or equal to N2. Okay, so, and then we want to show this part here. Okay, so we take this. Okay, so we know Gn greater than C1 times F of N, right? We do know that. Let me make this zoom out a little bit here. There we go. Okay, so that's what we know. And we'll continue this proof over here afterwards. Okay, so we have this statement. Now, let's see if you agree with me if we can just add F of N on both sides here. I think that works. And you know what? I'm just gonna move this over here so we have a bit more space. Okay, so that works. If we add F of N on both sides, then okay, so let's rewrite the left side. Now remember, the goal is to get to this, right? And we start with this. So okay, let's factor out F of N. Then you have C1 plus 1 times C1 plus 1 times F of N, right? Now, notice that if this C1 was instead C2, we would have our proof. It would be very convenient if we had this be C2. Well, seems like we can choose C2 here, so why don't we do that? And notice that we can let C2 be C1 plus 1 because we have access to it. We know that we know what C1 is, and it's the C1 is the C value that satisfies this statement, right? Okay. And then we can pick any number for N. I mean, 1 works out fine, right? So then we have our proof, and we can write, you know, here, like, since C2 equals C1 plus 1, and finished. Isn't that just wonderful?